Hi everyone, my name is Nicolás Rovira. I am a student of mechanical engineering of the Santo University in Bogota, Colombia, and I'm going to present my proposal that is called the design of a polygeneration system for an area of the Colombian Caribbean region. And this project was made also with the collaboration of Héctor Montaño, that is my director, and he's a mechanical engineer and currently he's a professor in the Santo University in Bogota, Colombia again. So, the content of the presentation in this slide, as you can see, we have the problem statement, the design methodology, the determination of energy potential, the result summary, the result analysis, the conclusions, and the reference. Okay, first of all, the problem statement. We know that all the sources used in the world are most uses the fossil fuels because the most source of energy that we have in the world. So for this kind of reason, the 80% of the energy sources used in the world are sourced by fossil fuels, and the other sources cover like only the 20% of the sources. But we have a really big problem with the fossil fuels because they account for about 60% of greenhouse gas emissions. So this is like we need to avoid this fossil fuel because it is dangerous with our planet. Another problem is that with one of each 7 people do not have access to electricity. So this is not in Colombia, this is in other world, and this is according to the information that the United Nations give us. And we also have the Sustainable Development Goals with the United Nations. That is, these are 17 Sustainable Development Goals, but in this case we focus on 3 specific goals. There are clean water and sanitation, affordable and no pollution energy, and climate action. Another problem, specifically in Colombia, is that 2.5 million people do not have access to electricity and 3.6 million people do not have access to safe drinking water. And specifically in the Caribbean region, 22.2% do not have access to safe drinking water. That is a big problem because it is above the national average, that is 20%. For this kind of reasons or problems, through the recent years, most of the nations use the renewable energies that with the objective to give electricity to the people with friendly sources and to avoid the fossil fuels. So these kind of energy sources are like solar energy, wind energy, biomass energy, and a process that is called desalination water to provide drinking water to the people. So again, through the recent years, a lot of nations have implemented the polygeneration system, that is like a system that integrate all or some energies, some renewable energies to generate a lot of products that will help the society. Uh, Once we already see all these problems, we need to actually stem the problem. So how do we do that? We do with this question, that is how to supply drinking water and electricity to a town in the Colombian Caribbean region through a polygeneration system. So first of all, we need to start with this. We select an area with their selection. So I need to mention that we we pre-select 4 areas that have like best the best characteristics to implement the polygeneration system. These pre-select areas uh, follow these 2 criteria. There is minimum wind speed of 4 meters per second and minimum solar irradiance of 4 kilowatts hours per square meters per day. So with these 2 criteria, we pre-select like for areas in the Caribbean region to select the area. So these 4 areas or towns are Santa Marta, Ciénaga, Uribe, and Providence and Saint Catalina. Once we have the pre-select areas, we use um, a selection alternative by weighting or ponderation. So we use other criteria besides the one that I already told you. There are wind rows, location, safe drinking water access, and electricity access. So wind rows, we focus that the wind always like be in only one direction. Location is that we seek that the area that we select have a lot of access to the highways and closeness with the sea in this case. The safe drinking water access, we seek the people of the percentage of people that doesn't have access to safe drinking water, and electricity the same thing. So we use this matrix and as you can see, we select Santa Marta because Santa Marta have the highest uh, ponderation or weight. So once we have Santa Marta, we search other sources that we can use or other processes that we can use in the polygeneration system. So I already told you that we want to implement wind energy and solar energy, and we search and we found that the biomass is a very good way to generate energy with like be friendly with the planet, and we also want to implement a sea aware desalinization because Santa Marta is a is an area that is close with the sea. So once we already have like all the sources that we want to implement in the polygeneration system, we make a scheme of the polygeneration system that we want. So in this case, as you can see, we have the wind turbines for the wind energy. We have the solar panels with solar energy that in this case is photovoltaic solar energy, and we have a Rankine cycle that we use the biomass of banana residue as full, and we use a boiler, a turbine, a condenser and pump, and a generator. Of course, we for generate electricity, and we have a desalination system. In this case, we use the reverse osmosis for desalinate the water. Okay, for the determination of energy potential, we start with energy, and we must to calculate the density of this area with this formula that is a formula closed with the ideal gas general formula, we calculate the density in this area, and after that we need to calculate the specific wind power with this equation, and we need to use the density that we already calculate and the speed of the velocity of the wind in this area. As you can see, this is the data that we collect, and once we have calculated the specific wind power, we need to calculate the power of the wind. As you can see, it's just multiply the specific wind power per the area, but in this case we doesn't have the area yet, so we need to select a wind turbine for any company that provide us an area of the blades. So we use the selection alternative of by ponderation with 2 criteria. Okay, we use these 3 criteria and we select a Siemens Gamesa wind turbine that is the most accurate wind turbine in this case. So once we have the wind turbine, we have the area, so we calculate the power of the wind of just one wind turbine, that is this power that you can see in the slide. And once we already have the power, we want an estimate area that we can put like some wind turbines. So we have a base area of 1.1 square kilometers. So as you can see, in this area fit 6 wind turbines. Of course, respectively the distance that the people recommended to the wind turbines distance. And in this base area we produce neither 4 megawatts. With the solar energy is like the inverse methodology. We first recopilate data for the NASA database, and with the minimum evidence per day that we recopilate with the NASA and the average temperature that we also recopilate of the NASA database, we pre-select some kinds of panel solars materials. In this case, the most accurate material is the polycrystalline silicon, because this material is like a better performance in the highest temperature. And with this material, we pre-select like 4 different panel solars, and with these 4 criteria, we select that the best way in this case is the Canadian solar panel solar for this situation. And we have already the panel solar selection formula, as you can see. So with this formula we calculate the power out. As you know, in a panel solar the current is directly, but most of the equipments that we use in our lives have alternative current, so we need to like invert this current, and this invert have a loss of 5% of the power out. So we calculate that power is that you can see in the slide, and after that, with the solar peak hours, we calculate that one module can generate this amount per day. So with the energy demand of Santa Marta, with the 30% of the energy demand, that is that, as you can see that in the slide, we and with the power out we calculate the models that we need to implement in the solar in the polygeneration system to cover the 30% energy demand. So with these two data we calculate this amount of models, and with the peak solar hours and again with the energy demand we calculate the energy produced by all these models. Okay, with the biomass energy we found that in this case in this area there's a lot of waste of bananas, so we use this biomass. So in this case we have banana ranches and the stem of the banana plants, and we also have the rejection banana, that is like the banana that we can eat. So we need to calculate the dry residue mass with for each residue. In this case, banana ranches, banana stem, rejection banana. And we use this formula with the area, that is a generic data, the performance of the cultive, that is also a generic data, and with the residue factor, that is this, and the dry residue fraction, that is this. So we calculate for each one and we add up all three residues to have this dry residue mass, that is the units are tons per year. And after that we calculate the energy potential of this type of biomass, that is, as you can see, like 50 megawatts or 1,582.49 terajoules per year. So once we have this energy potential, we need to calculate the thermoelectric, like so for the thermoelectric plant we calculate, we need to select first the boiler. So we select the boiler with these two criteria: that produces the steam capacity and the thermal efficiency, and we select that the best way is the Southern Boiler Company, that provides a good way to boil our biomass. And after that we need to select a turbine with these four criteria: that inlet pressure and temperature, exhaust pressure, rated power, and cost. And with these four criteria we select that the best way is that the turbine that Shanghai Electric Company offered to us with this data. And once we have these two equipments, we have like a first ranking cycle and like an exercise, and as you can see in the slide, and we calculate the ranking cycle with all the thermodynamic characteristics, and we calculate this ranking cycle. Once we have the ranking cycle, we need to calculate the pump. We need to select the pump, of course. We already have like an scheme of this ranking cycle, but we need to select the pump that is the most accurate pump for this case. So as you know, the pump need to have a higher flow and a higher operation pressure to provide the water to the boiler. So we have this unifilar diagram, and with this flow and this operating pressure that we calculate previously, we calculate the minimum diameter with this formula, and we calculate that the speed of this in this the speed between the condenser and the boiler need to be this one, and the nominal diameter is 4-inch scribble fork with the, of course, the piper, and we need to calculate the head of the pump, of course, with with these formulas. We calculate that the head of the pump is this, as you can see in the slide, and we with this head and the flow rate that we have here, we select that the SAR electropump company is the best way in this case. Desalinate water production. So with the average consumption in the Santa Marta and the 50% of households, we have like two criteria to calculate our desalinated water production system. We want like a desired product flow rate, so we need to have our decision to desired product flow rate. So it's like data that we defined previously, and with these four criteria, we select a membrane that like accommodate to this desired product flow rate and these other criteria. We found that the film tank membranes is the best way in this case, and with the a national institute in Bemar, that is like an institution that regulate all the compounds in the water. We found that the most common compounds in the sea water of the Santa Marta are chlorine, sodium, and sulfate. So after that, we have with the technical of the membranes, we have an active area of 41 square meters and a permit flow of, as you can see in the slide. And with these three data, we use the software EES to calculate that. For this desired flow rate, we need to have these membranes, these pressure tubes, and the consumption of the pump in this system is as you can see in the slide. We have like a summary of the result of the polygeneration system. The solar energy with all these modules is 3 megawatts. The wind energy production is this with 6 wind turbines. The biomass energy is with the Rankine cycle is this one. The desalination membranes is the one that I already show you, and the total of the electrical energy is 15.79 megawatts. That is a lot, I think. Okay, we have like a global analysis. First of all, the system produced 15.79 megawatts. That is like this per year. A surplus of 5.555 megawatts will remain because we have like already covered all the demand of the electricity axis, so we have this surplus. We know that Colombia is currently beating of wind and solar energy, so I think that this kind of projects have like a lot of interest in for the Colombian government, and we compared this system with another polygeneration system, and we found that we have 80% more than the hybrid solar biomass polygeneration system in India, 80% of the energy, of course. We do that like equipment costing, and the first inversion that we need to do is almost 22 million of dollars. Of course, we don't include in this costing like the maintenance, the implement of these kind of equipments and all these kind of things. So finally, we have the conclusion of the summary of the project. First of all, the municipality or the town or the area that present the best conditions for the implementation of a full generation system was Santa Marta due to the energy potential that presents, also for the strategic geographical location and the number of possible people benefit by the project. Due to the geographical location of Santa Marta, it is possible to use the residue of banana crops generated in the this is the second one, sorry. Due to the geographical location of Santa Marta, it is possible to use the residues of banana crops generated in the department of Magdalena, which can be used as a renewable energy source for the production of electricity through a power cycle. Okay, the third one, taking into account the deficit in the drinking water service in the town of Santa Marta, a process of desalination was improved in the polygeneration plant. The production of electricity from wind energy was calculated at 729.38 kilowatts, which is approximately 50% of the maximum capacity of the wind turbines of the Hepirachi wind farm in La Guajira. However, it should be taken into account in mind that the wind speed in Santa Marta may be higher at other times of the year, which will imply a maximum production of up to 2.2 megawatts per wind turbine. The fifth one, the design photovoltaic installation has the capacity to produce 3 megawatts since only this amount of panels. However, if we use all these panels of the solar park in El Paso Cesar, I'm sorry, we will generate approximately this amount. Okay, the power cycle that has banana waste biomass as full will produce this power. It is similar to the generation of each engine of the thermonuclear plant of 80.8 megawatts located in an area near Santa Marta. The reverse osmosis desalination process will generate a drinking water production of this amount at a low cost, is very low, of approximately 0.49 kilowatts per hour per cube meter. In addition, when compared with La Guajira desalination plant, it is evident that the system design is equivalent to more than 280 Manauro plants. And the thermoelectric plants allows not only to produce electrical energy for the city's network, but also feed the reverse osmosis of the desalination system, which consumes only 90% of the electricity produced in this system. The polygeneration system produces a total of this amount of electricity with the benefits of produce this amount of drinking water, which could grant access to this resource to 3,023 and another 12,824 families respectively, which makes the project attractive with an initial investment of the equipment of almost $22 million that I already told you. Reasonable cost compared to similar projects such as a Helipachi wind farm, which had an initial invest of $21 million with an installed capacity of 19.5 megawatts. So that's it. That's my proposal, that's my project, and I hope that you like it. This is the reference of my project. And if you have any question, please let me know. And thank you for your attention. Bye.